Okay, and a refresher on rational functions. Rational functions, functions of the form p of x over q of x. P of x and q of x here are representing polynomial functions, which we saw in previous videos. And we also have to make sure that q of x is not 0, because otherwise dividing by 0, bad things happen. So again, to obtain or to really analyze a rational function and determine its properties, we have a set of steps that we kind of want to follow. You don't have to follow them precisely, but it's a good kind of problem-solving process. First thing is to factor p of x and q of x completely. State the domain. Okay, so typically the domain is going to be all real numbers, which, if you've seen the symbol double bar r, that means all real numbers. So you can say all real numbers except whatever x values make q of x equal to 0. Okay, and then we'll cancel and get a reduced form. Determine vertical asymptotes, holes, and horizontal asymptotes, and then we have a few different cases that we need to consider for the horizontal asymptote. Okay, so let's actually just go through a problem. So we have the following function. We want to determine its domain, reduced form, vertical asymptotes, holes, horizontal asymptotes, and then there I added in an extra part where we have to identify the x-intercepts. Okay, so first thing is we want to try and factor this. Okay, so let's see, I'll have a 3, and I'm just going to look at the numerator first. 3x plus 1, and then now this second term factors as x plus 3 and x minus 2. Okay, and then the denominator factors as x minus 2, and then this factors as x minus 2, x plus 1. Okay, so now I've achieved step 1, I've factored. Okay, and now before I move on, step 2 said I should state the domain. Okay, so it's going to be, and I'm just going to use double bar r for all real numbers. If it's easier for you to write it out, feel free to. And then I'm going to say except, take away, and then I'm going to use a set bracket, a squiggly bracket, and then look at all the values that would make the denominator 0, and that's currently positive 2, because that would make that 0 and that 0, or negative 1. Okay. Now another equivalent way to write this, and I should be using the set bracket here, another equivalent way to write this is to use interval notation. You could say minus infinity to minus 1, union minus 1 to 2, union 2 to infinity. And there we go. Okay, so now I've stated the domain. I can actually do any cancellation now if I want. So let's see, what factors do I have in common? I have an x plus 1 in common in the numerator and denominator, and 1 x minus 2. Okay, so I can cancel that. And my reduced form, r of x, is just going to equal 3 parentheses x plus 3 over x minus 2. Okay, and now from here on out, I can do everything with my reduced form. It's a lot easier and a lot quicker, but if you want to work with the original function, feel free to. Now vertical asymptotes, up above, it says that vertical asymptotes come from the reduced form. Okay, so what values make the reduced form undefined? And this is just 2. So I have a vertical asymptote at when x is equal to 2. Holes, okay, let's go up and refresh our memory on what holes are. Okay, holes are x values which are not vertical asymptotes, but are not in the domain. So in my domain, I had to exclude 2 and minus 1. 2 was a vertical asymptote and was excluded. Minus 1 is the only other value that I had to exclude from my domain. So, but it's not a vertical asymptote, so therefore it's a hole. So I plug in minus 1, and now to find the y value, I always want to list my hole as a coordinate pair. To find the y value, simply plug in negative 1 up here. So let's see, that'll be 3 times a positive 2. So that's 6 in the numerator over and minus 3 in the denominator. So a 6 over minus 3 is a minus 2. Okay, and the horizontal asymptote. Now here, I have to look at the degree. I have to look at the degree of the numerator and the degree of the denominator. So the degree of the numerator, and I can either look in the reduced form or the original function. Doesn't much matter. I'm going to look at the reduced form because it's easier. So the degree of the numerator is 1, and the degree of the denominator is also 1. Okay, so I go up to my number 6, and it says, okay, well, no, the 2 degrees, n is not greater than m. The numerator is not greater than the denominator. Numerator is not less than the denominator, but they are equal. Okay, so the horizontal asymptote is the ratio of the leading coefficients. Okay, so the ratio is going to be y is equal to, and the coefficient in the numerator is 3. Denominator coefficient is just 1. So it's just 3. Okay, and x-intercept, here this only comes from whatever would make the numerator equal 0. So negative 3. So I would have, as a coordinate pair, I would have an x value of minus 3, y value of 0. Okay, and then if you wish to continue, you can certainly obtain a sketch of the graph for this rational function. The intent here was just to go through and identify these different properties. Stay tuned for exponential functions.